Hello, everyone. My name is Yunus Emre. First of all, I would like to thank the organization for giving the opportunity to study with such talented and ambitious young mathematicians. Of course, one of them is Arsen. He's studying mathematics at Middle East Technical University, and together we studied graph theory, and he will present some topics today. And thank you. You can start, Arsen.
Thank you very much, Yunus Emre Hocam. As my mentor mentioned, today I will be talking about random graphs and random walks. Here are my main references. We have studied Ramsey theory and random graphs from some sections of the book Modern Graph Theory by Bolabas. And we have also studied lecture notes of Serdar Yüksel for random graphs, random walks part. And Serdar Yüksel is also PhD supervisor of my mentor, Yunus Emre Hoca. Here I will be talking about Ramsey theory first. Actually, Ramsey theory is not directly associated with random graphs and random walks. But in order to give motivation for random graphs, I prefer talking about Ramsey theory first.
O tuşa bir daha basarsan da aşağıdaki iki monitörden biri.
Okay. So Ramsey theory actually asks a very general question in mathematics, and this question is how big a mathematical object should be in order to have a certain property. Like this property can be anything you can think of. Therefore, this is a very general question. But we will be interested in a graph theory question here. And this will lead us to definition of Ramsey number. Ramsey number is the minimum number n such that any red-blue coloring of red-blue edge coloring of complete graph on m vertices, this is denoted by Kn, has either a red Ks or a blue Kt. And this number is denoted by RST. And there are some simple properties such as RST is equal to RTS by symmetry, basically. And RS2 equals S equals R2S. These are some simple properties of Ramsey number. And here we have a very natural upper bound on Ramsey numbers for general Ramsey numbers, actually. Here we have this upper bound, RST is less than or equal to RS minus 1t plus RST minus 1. This one is a recursive relation, actually, a recursive inequality. But by using Pascal's identity here, we can make a compact form for an upper bound on RST again. And the second inequality also implies that RST is finite, of course. But this is not actually in first glance obvious, because there may have been a case where we are just making the graph larger, but still we have no red Ks or blue Kt. But this says that it is always finite. And here's some example of Ramsey number. And for instance, if I choose like randomly 6 people out of you, then I can claim that either there are 3 of you who know all each other, like 2, they know, you all know each other, or you all stranger to each other. And I can't do this for 5 people. I mean, I can, but this is not guaranteed. But for 6 people, it is guaranteed. And this is also a Ramsey theory problem. This is actually as same as stating that R33 is equal to 6. Actually, I gave a long proof here to give the main idea of Ramsey theory. This is a very general idea here, and one can see this idea in many Ramsey theory problems, many Ramsey theory proofs. I will skip it for now, but if I have some time left, I will come back to this. And here are some theorems on some Ramsey numbers. Here, notice that these numbers, like, first of all, R is small here. The notation was with big R. This has a reason because Ramsey numbers can also be generalized to not only to complete graphs, but also any graph. Like if we take H1 and H2, then we can also ask what is the minimum number n such that any red-blue edge coloring of Kn contains a red H1 or blue H2. And here there are some examples. For instance, the second theorem, there is a complete graph and the tree. And these Ramsey numbers are certain. They are not bounds. So these are some actually strong theorems, and their proofs were a little long, but the idea of their proofs will be the same as this idea here, if I could explain later. And now we are ready to get into random graphs, one of our main topics. Actually, the random graph concept is emerged from, like, its origin is from a series of papers written by Erdos and Renyi, and they start in 1959. But there are also some usage of random graphs before this year. But they are the pioneers of the theory, we can say. So what we need to do in order to talk about some randomness, we need, of course, a probability space. And in order to do this, when we are given a set of graphs, we need to make it into a probability space by defining a measure on it. Here, measure theory is a little complicated, so I will give simply how we can construct these probability spaces. And we will mainly only interested in the first probability space here, GMP. And these are just the probability space of graphs on M vertices, which where any edge is chosen with probability P and not chosen with probability 1 minus P. And we generally write Q for 1 minus P. And the other ones are different natural ideas to construct these probability spaces. And here, if we can define a probability space, we can talk about random variables, of course. And if we talk about random variables, then we can also look at their expectations. So here, in order to prove our main result on random graphs, we will use this expectation concept. And here we define two random variables, xs and xs prime, where xs is the number of complete subgraphs ks in a random graph GP. Like GP is an element of probability space GMP actually here. And xs prime is the number of complete subgraphs ks in complement of this GP graph. And this will be useful for us because we talked about Ramsey number, and Ramsey number is for two edge colorings of graphs. So we can also think this problem as a graph having ks or its complement having kt. These are equivalent problems here, so these definitions actually make sense. And here's a very simple lemma on expectation of these random variables. And these are the formulas for the expectations. They are simple to deduce actually here. And this theorem is our actually main theorem. Is given by Erdos, and this theorem states that under certain conditions given here, then we can put a lower bound on RSS, and by using the same idea, we can also put a lower bound on RST here. Like the lower bounds are the same, but conditions are a little different. But this is very important, as you will see on the example that I skipped. There may be some problems constructing these lower bounds, constructing graphs that give some lower bounds. Since the proof of this theorem for part 1, part 2 has the same idea, is elegant one, I will give it here. Here we consider a special probability space Gn1/2. This is a very special probability space because normally in GMP, not every random graph is equiprobable. Like when we choose a random graph for arbitrary p, it may not have the same probability as another graph that we choose. They are equiprobable if and only if they have the same number of edges, actually. But for Gn1/2, every graph here is equiprobable. And this probability is basically like number of edges choose to 2 to the power minus number of edges choose to. And here we found expectation formula in previous lemma. So we can write expectation of xs plus xs prime here. As this, and by assumption, this value is less than 1 here. But this means there should be a graph in GMP, Gn1/2 actually, such that this sum, it is mapped to 0. Like this is mainly because these numbers, xs and xs prime, are actually non-negative integers, of course. Otherwise, we can't just say that expectation less than 1 means their sum should be 0 for some graph. But here, so where does it cut? I can turn back and.
I think wasn't a big issue. We were just explaining the protocol. I think you can continue.
Okay, no problem. Okay. And here are also some theorems by which were proven by using expectation and random graphs. I put these because I think these are interesting. Like these are normally pure graph theoretic statements, but they are proven using random graphs and expectation concept, as Erdos gave a proof for lower bound on Ramsey numbers. The first one is about bipartite graphs, and the second one actually is easier to understand. The first one is a little complicated, but for the second one, it is about existence of a graph with certain chromatic number and girth. Girth means here the length of the smallest cycle in a graph. and chromatic number is the smallest number of colors needed in order to properly color a graph's vertices. And this is about existence of a certain graph with certain order. So here there is another interesting concept, this almost all concept, I'd say. And this concept is defined as when we are given a property, let's say Q, then we say that almost every graph in our probability space GP has this property Q if this limit tends to 1. This may not seem concrete at first glance, but there are actually some examples that you may know. For instance, maybe most of you heard that most of the matrices have non-zero determinants, like a statement like this. Actually, this can be restated as almost every matrix has non-zero determinants. Because if we look at this limit on, for instance, the size of matrix, or if we are looking for some infinite field, then we can first count the matrices with non-zero determinant in a finite field, let's say in F2, for instance. Then we can take its limits when this order of field goes to infinity. Then we will get 1 each time. And this is why they say almost every matrix has non-zero determinants, and or you can say that if we choose a matrix randomly, then it is highly probable that you will get a matrix with non-zero determinants. And there are some simple properties for, of course, our random graph concepts as well. And one of them is if we fix a graph H, then almost every graph in GMP contains H as a span subgraph. And this is also one of the results using this almost all concept. And here are some properties which holds for almost all graphs, and the last one holds for almost no graph, actually. I gave them as examples since their proofs are a little messy, let's say. And finally, our last topic is random walks. Here, in order to define a random walk, we need to first define a stochastic process, what stochastic process means. And it normally has a really overwhelming definition about like sigma algebras and some major theory stuff. But here, to put it simply, we can say that a stochastic process is a sequence of some random variables. And Markov chain is a very special stochastic process where the probability of passing to another state only depends on the current state. And we can also define random walk on Markov chains by just saying that random walk is a Markov we will be only depends on our current state here. I mean, we can't just go to, for instance, dinner room in one step. So it only depends on our current state. And here is the formal expression for this example, let's say. And this example is was given by my mentor to me while we were studying random walks. And we have a cube graph here. 2 points are fixed, O and S. Then we are starting a random walk from O. And the probability that we pass to each vertex is equal here, at least to adjacent vertices are equal, of course. Then we are asked to find expected number of steps to getting back to O. Like after average, how many steps we get back to O when we start from O. And there are other two questions here. Here's a solution. This idea also mainly used in some Markov chain problems. Right now, I don't have some time, I think, so I'll just skip it. If anyone wants to ask it after the presentation, I'll gladly answer it. And here's a application of random walks to electrical circuits. This one is actually interesting, and it was groundbreaking for me, because normally in this circuit, we know that by Ohm's law and by some circuit analysis, we can just say that there's 2 ampere current going through 1 ohm resistance and 1 ampere current going through 2 ohm resistance. But I mean, current is not some intelligent creature that can decide how to split on that intersection point. Like it can't just say that I'll give 2 to this side and 1 to this side, but it's actually randomly walking through this circuit. But the values that we generally analyze we found by analyzing the circuit are expected values of the current on those points. So this is actually a random walk on a circuit, and by using this idea, we can also prove Kirchhoff's current law and Kirchhoff's voltage law mathematically. And that's all for me. Thank you for listening.